Okay, good afternoon, everybody. We're going to be doing section 1.5 here. New week, new packet. So let's go ahead and dive right into it. So this very first section, it says the same sequence is shown in both table and graph. So this table is the same as this graph. Indicate on the table where you see the rate of change of the sequence. Then draw on the graph where you see the rate of change. And so typically when we talk about rate of change, you may have heard this written another way, so that rate of change is the same thing as slope, or sometimes you'll see y equals mx plus b. We call it m. But it's also, another way of thinking about it is our change in y, over our change in x. And so this triangle is a scientific symbol. It's actually the Greek letter delta, and that means change. So change in y over change in x. Sometimes we call that rise over run. Okay. So when we look at this, when I look at this, it doesn't have x and y, but I know that my n is essentially my x and my f of n is my y. So I'm going to look for my change in y. And when I look at my change in y, I see that each time I'm going up 3, right? Plus 3, plus 3, plus 3. And for every time I go up 3, my x goes up plus 1, plus 1. So I know that it is 3 over 1, or we can simplify that fraction to just be 3. And so we have shown how we see that, 3 over 1. Now when I look at the graph, I have to show this rise over run as well. So as I go from one point, I go up 3 and over 1, so that this plus 3 is linked here, and this plus 1 is linked here. So that is where I see the 3 and 1, and 3 and 1, and 3 and 1. And so I'm asking you pretty much to do exactly that. Show that relationship, draw the lines between them so that we know how they're relating to each other. Okay, so that's going to work for 1, 2, 3, and 4. When we turn the page, we have another group of problems, and it says this time we're working with recursive and explicit functions of geometric sequences. So you're going to have to refer to what we did on the board today in class. Now it says below you're given various types of information. Write the recursive and explicit functions for each geometric. So geometric tells us right away, geometric means we're going to be multiplying or dividing to go from one sequence to another. So when I look at number 5, I have my sequence 2, 4, 8, 16. And so I have to see what is my pattern, and I can very quickly tell that I'm multiplying by 2 at each time. All right, so now it asks us to graph it. So if at 1 I'm at 2, if at 2 I'm at 3, 4, at 3 I'm at 5, 6, 7, 8. You can see how quickly this begins to grow. 8. At 4, this is my fourth one, I'm at like 16, 9, 10, 11, 12, 13, 14, 15, 16. I'm already off the graph. So you can kind of see how quickly that grows. Recursively, I know that f of x is the previous step, f of x minus 1, and then each time I'm timesing by 2. So I just have to write times 2. Because remember, our general form, right? This would be a good time to write that generalization down. Our general form for geometric recursive is always going to be f of x equals f of x minus 1 times our common ratio. Okay? So this will change based on the problem. But this will always be the same. Always the same. So we have that. I'll just put that right there. But now we want to know what the explicit is. I can go ahead and zoom in a little bit, I'm sure. So you guys can kind of see this just a little bit better. Let's focus it. All right. So now explicitly, well, this time, remember I have to go f of x equals, in my general form, my geometric explicit general form is going to be f of x equals our first term times our common ratio to the x minus 1 power. Okay, so that way we can use this formula to figure out what's going on here. So when I look at this problem, I have to look at what my first term was, which I covered up with this post-it, but I can see my first term was 2 times my common ratio, which I also know is 2, to the x minus 1 power. And so that's one way of writing it. It just so happens we could even simplify this further to just 2 to the x because our first term happens to be our common ratio. But if that wasn't the case, we would use this model here to be able to do that. Alrighty, so with that said, let me sticky note this here. So now that we have our general forms and we've applied it, I expect you to do it for the other ones. When we turn the page, it's more of the same, except this time we have arithmetic sequences here. And so for this one, remember for our arithmetic sequences, we're looking for arithmetic means we are adding or subtracting from one step to another. So I look here, I go 2 to 4 to 6 to 8, I see that I'm adding 2. And so that add 2 is my common difference. Okay? And so I'll let you graph that on your own because I think the recursive and explicit's the tough part. Recursively, we're going to say f of x is the previous step, f of x minus 1, but each time we're adding the common difference. So we're going to add 2 to each step. And in fact, our general form of this, so our general arithmetic recursive is going to be f of x equals f of x minus 1 plus the common difference. And we're going to call that good like that. And so now for the explicit, it's f of x equals our common difference times x plus our 0th term, So when I look at this, I know that f of x is going to equal my common difference, which is 2, x. And then I need to figure out what my 0th term is. And I look here, and I know if I add 2 to get my 0th term, I have to subtract 2, which would have given me 0. So plus 0. But I don't even have to write plus 0. So I can just simplify this as simply f of x equals 2x. And that'll be done. Alright, I think that's it. Do I have any more for you? Nope, it's just more of the same. So those are your major types of problems. I expect recursive and explicit to be difficult, and I expect that these here, for explicit arithmetic and recursive arithmetic, these are going to be important to know and build, and likewise with geometric, the explicit and recursive. It's going to be important to know these yellow sticky notes and build. So make sure you look those over, have them in your notes, and do those problems, and we can come back tomorrow and work on them. Thank you so much, and good luck on that homework.